welcome to this presentation. I hope you had a nice lunch, everyone. Today I will talk about the MIDI2 in the real world with Zephyr. So first of all, I'm Titouan. I work at MIDI2, which is a company based in Belgium doing open source embedded software. These days I mostly work on the Beatroot, the LTS maintenance program, but I'm also like playing around with Zephyr and contributing some things. And besides that, I also have some classical music background, maybe. So, first of all, let's talk about MIDI itself. MIDI, it's a protocol born in the 80s. It's an old thing intended to connect controllers, like things, keyboard, knob sliders, to synthesizers, some things that will produce some sound out of note events. You may recognize the iconic DIN5 connector, which is pretty much the MIDI icon these days. And the hood, it's simply a UART at 31.25 kilobits per second, and it's unidirectional, so you get from one output to the synthesizer input. And also there's the daisy chaining, so most synthesizer will have a MIDI through port, which is simply electrically connected from the input to the output. And so you can create some kind of MIDI bus where you can connect many instruments together. But yet it's still unidirectional. Since we have many synthesizers connected together on the same bus, we need to have a way to address them differently. So in MIDI, there are up to 16 channels. And so synthesizer can choose to have one channel or listen to all of them, and similarly on the senders, on the control side. To do that, some old synthesizer will have a physical switch like this, where you can select the MIDI channel. Otherwise, you can select it in software, or they can simply listen to all channels together. What we send as MIDI message, first of all, there are I would say the most important one, which are the channel voice messages. So you have the not on or not off event, which is to play notes. And what we must remember in MIDI1 is that we only have 7 bits of useful data. The first, the most significant bit, if set, means start of message. So you can see all the comments on the first byte here. They have the most significant bit set. So not on, not off are 8 or 9, and then you have 2 parameters like the note number, and which note to play on the keyboard, and the velocity, which is how hard you press the key. So you can put some nuance in the notes that you play. There are also the control change, like knobs and sliders to control other parameters. Also the program change, which means you can tell the synthesizer to change the sound it will play. And the pitch bends, so this is used if you have like a guitar, for instance, you push the string, this will pitch up the notes, and you can express that in MIDI using the pitch bend message. Then we have the system exclusive message, which are a bit special, and they allow to convey some arbitrary data on the bus from, like for instance, to reprogram a synthesizer or things. And they are a bit special in that you have the F0 start byte, and then any number of arbitrary 7 bits numbers, and finally the end of system exclusive message, which ends the transmission. And then there are some system real-time messages like the clock, which allows to synchronize synthesizer. If you have some audio effects like a delay, a chorus, or things, they can be synchronized across synthesizer. And also if you have a controller in your studio to start or play on the controls, then there are also some messages for that. So if you look at MIDI sequencer, as you may recognize these kind of shapes, so you see the notes, and then, as I said, you have the notes on when the note starts, not off when the note ends, logically. Then you have the note number, which is represented on the keyboard on the left, and then the velocity on the scale below. And again, you have the controls. You can send some play stop from your MIDI controller, or the clock, which can be seen here in the lower right corner. Some example MIDI message, like start playing a note, it's 90, 46, 63, which means that, okay, you won't be reading MIDI by hand, I hope. But also you can simply load a program, start to play or stop, or send a system exclusive message like that. So these are very basic examples, but you can see here the takeaway is that you see it's a variable length message and it's kind of stream oriented. In the 2020s came the new revision of the protocol, which is called MIDI2. And in that realm, we are having some UMP endpoints. I will come back on that just afterwards. But basically, a UMP endpoint is where you deliver some MIDI2 messages. A UMP endpoint has 16 groups, and each of them has 16 channels. And a UMP endpoint must be bidirectional, so you can send and receive data from there. So why do we have 16 groups? It's because you can kind of hook up some MIDI ports on top of these groups. So you can, for instance, map a bidirectional port on group number 14 and an input and an output on a different group. But you can also have some synthesizer which have more voices and stuff on the function block, which we'll use then, in this case, 3 groups. And so what are we going to send as data in MIDI2? So now we have the universal MIDI packets, hence the name UMP. This is now a fixed length packet, so it's aligned on 4 bytes. So we have first a field in here, which is the message type, which identifies how lengthy is that packet. So it's fixed size in that the message type determines how much data you are going to have then. And it's 1 to 4 words of these 4 bytes words. So here, for instance, the notes off message in MIDI2 starts with message type 4, which means MIDI2, then the group number, to which group in the UMP endpoint you are going to deliver that. Then we have the identifier, the command for notes off, which is 8 in that case, like in MIDI1. Then the MIDI1 channel number, then a note number. And then in MIDI2, we have now the velocity, which is on 16 bits instead of 7. So we have more expressivity, more range to express different nuances of notes. And also there's a new attribute thing, which is you can put several different things in there. So you have, depending on the attribute type, one example of that is called pitch 7.9. So it's the attribute type 3. And this allows you to have more fine-grained notes. So you can play now notes that are in between the piano keys, I would say. So it's expressed as a Q709 fixed point number. So you have the MIDI note number on the blue part on the left, and then a fractional part up to the next note, up to the next MIDI note over there. So if we look at those 2 notes in a partition, I don't know if you can read music, but yeah, if you ask a keyboardist, it will probably say, okay, this is the same note, so this is this one, G sharp or A flat. But if you ask a violinist, then it can play 2 different notes for that, for these notes. And so the pitch 709 allows to encode more precise scales or to play some microtonal music, which is common in non-Western music, I would say. Another thing you can encode in those attributes is the articulation. So if you are composing some film music, for instance, when you have lots of instruments, like strings, some classical drums and that kind of things, then you can also make more nuance on what you are going to play. Like, are you going to play them legato, staccato, and all that kind of articulation? But you can also specify the direction of plucking or bowing on the string, and also which string to use, so it can make different sounds. For instance, on the guitar, you can play the same notes on different strings at different position, but the sound will be different because the length of the string is different. And so, yeah, if you see that partition, you have on the left the 3 notes which are legato, indicated by that blah, blah, blah. And the last one is staccato, so it means da, 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 da. Okay. And then in MIDI2, you can, in the UMP format, you can still encode MIDI1 message, so it's very simple. You have the message type 2, which indicates MIDI1 data. Then again, the UMP group to which you're delivering that message. And then simply you put the 3 bytes channel voice message we saw earlier simply just afterwards. Some example again. So this was the same noton as a few slides ago. So in MIDI1, we can deliver that message to group number 5. So musician, when they use music software, they start counting from 1. We are programmers, so we start counting at 0. So this will be confusing in all the following slides, I guess. But yeah, so this means we are delivering that play note message to group 5 on the first channel. And in MIDI2, we can have a more complex example. So here we are playing a note which is outside of the classical MIDI range keyboard. And so this one says we are playing that note with whatever you see on the slide. So now we have seen what kind of data we are going to transport. Let's use, for instance, USB to deliver them. So just a note, I already made a few talks about that. One at FOSDEM, which was mostly about the USB MIDI device class. And another one at my company, which you can also find on the web, which is more focused on how to implement actually that USB device. So USB MIDI, there was a first specification in the late 90s. So it was a bit convoluted. So the USB MIDI function is now specified as having some MIDI inputs and outputs. Some of them are external, which means connected to the world. And some of them are embedded, which means they are connected to the USB, so they can be connected to your computer, ultimately. So, for example, if we have a keyboard which is playing some notes towards your computer, first it comes from the external MIDI in, then goes to the embedded MIDI out, because it gets out of the MIDI function, then goes through a USB endpoint to your computer. And conversely, if you want to send some data, you see it's the inverse data path. But as you can see, it's a bit confusing because you have inputs, outputs, and all of this is in a big soup, I would say. But anyway, this allows to describe many different topologies. So you have the classical MIDI in-out converter, which is basically the thing you would have in USB on your desk. But also, interestingly enough, you can describe things like a USB MIDI interface that has an external MIDI in that goes directly to an external MIDI out, which is actually a MIDI through, and that could even not go to your computer. You can do that in USB MIDI 1. And also, the specification has a complex example, whatever that says. But in practice, every single device I had in my hand always implemented that topology, so it was a bit overkill. The USB MIDI one. In 2020, along with the UMP spec, came the USB MIDI 2.0 specification, which greatly simplifies the operational model. So now it's simple. You have one USB endpoint correspond to one UMP endpoint. Anyway, the spec requires that you still have on alt setting 0 in USB, a USB MIDI 1.0 interface declared for backward compatibility. So if we want to now have the things that are described, we have now the concept of group terminal blocks, which are mapped to the UMP functional blocks. It's pretty much interchangeable in that manner. And if we have this, for instance, which has 2 inputs and 2 output terminals, it means that we have a pair of data coming from the same instrument, a pair of pipes of data going to the instruments, but ultimately having all of this in the same block means that it's a single device that's gonna be connected. So you can send and receive from the same instrument or device. So why using Zephyr here? We're in the Zephyr dev room, so I don't have to convince you anymore. We get all the niceties from Zephyr, like USB, network, possibly other network helpers. We also have all the things like the logging, the shell, input, crypto, whatever you want. And all the tooling like kconfig, the device tree, West, whatever you like. On my side, I really love the device tree feature. So the operational model in USB MIDI in Zephyr is that, so you have that UMP packet, which is very simple in that case. And then your application will be able to exchange the 16 UMP group with a host. So it's implemented in the USB MIDI class, and all of that is wrapped into a USB MIDI device, so we can use the standard device API from Zephyr. So how that works, you can use USB-D MIDI send, which sends a message. And you can also register a callback. So when the host has some data to send, some UMP packets, you receive them through a callback. I choose not to have like a buffer or something, so you can react in real time. If you want some buffering, just do it in your application. It's very minimal, a thin layer. There's also a sample if you want to see more. So to set up Zephyr with USB MIDI, so if you want that block, by the way, this graph comes from the specification, so I'm just reusing things. So yeah, it relates to what's already available in public documents. But first of all, we enable those two kconfigs options, so USB device stack next, and the USB-D MIDI class. Then we are going to introduce a MIDI2 device in the device tree. So it's simply having that's compatible, and yeah, everything is basically empty for now. Then to describe, for instance, that first block with two UMP groups, which in the UMP endpoint graph looks like this. So we introduce a new node under the MIDI2 device, which is the block 1 in this case. It starts at UMP group 1. It spans two groups, again, 0 to 1, because musician versus programmers. In that case, we can say that it's a bidirectional terminal, and it conveys MIDI2 data. Also, on block 3, which has an external MIDI1 input, we can also say start at group 3, only one group wide this time. It conveys up to 64 bits MIDI1 data. It's an input only, and also we can specify that this is connected to an actual MIDI port, so it's limited in speed to 31.25 kilobits per second, which the host can use, especially in output ports, to limit the traffic, to not overrun your device. So if you want to implement a simple MIDI keyboard, like pressing some keys that will be sending events to my computer, we are going to leverage the input subsystem from Zephyr. So we just can define an input callback, which will call a function where a GPIO is enabled, like if you press a button. In this case, the first thing is, since MIDI nodes are up to 7 bits, we just check that we're in range. Yeah. Then if we press the key, it's a not on. If we release the key, it's a not off. And we can use the key number to know the note, the MIDI note to send. Then we can use the macro UMP MIDI1 channel voice to create the UMP packet for us. We can set it to UMP group number 3, which is 2 for us programmers, on the MIDI channel 1, which is 0 for us programmers, and we can set an arbitrary velocity here, 100 on 127. It's quite fortissimo, I would say. And then finally, we just send it to the host, and it will be conveyed over USB. Since USB is driven by the host, so from the point of view of the device, we're not always enabled. So the host must select our interface and must enumerate us so we can start to exchange some data. And to that end, the USB MIDI device has a ready callback. So this will be called when the MIDI2 interface has been selected and enabled by the host. And in that case, we can simply, for instance, light up a LED. So my board will blink, or simply, not blink in that case, but will be light when the interface is up. And also, as I said, we have the receive callback, and then simply, if we want to implement a synthesizer on that side of the device, we have that receive callback. First of all, we can check that we're receiving actually a UMP MIDI2 event. Then, since we now have two UMP groups, we can build some kind of channel which is up to 32, since we have 2 times 16 channels. And then, depending on the MIDI command, if it's a note on, we can start playing a tone, or if it's a note off, we stop playing that tone on the given channel. And let's just assume we have some tone generators. So, a demo. I have this on my desk. So, as you can see, I have the ST-Link port, which is just used for power supply. We have the user LED, which is yellow if connected to my host. I have a user button, which is the keyboard. and then the USB MIDI to my computer, and some audio outputs. So you can see here on the left, I'm not sure if that's readable for you, but we have a MIDI sequencer, and then on the right, I have a script to run my demo, so it's easier for me to present. So you can see my MIDI interface here. We have the two groups I described in the device tree. So the synthesizer, which has two groups, and the keyboard only on group 3. I can read some UMP events. So in Linux, you can use dev-snd and just read the UMP packets like that. So I can also record them here, I think. So if I press the button, okay, so I make some notes. That's very nice. It also appears in the old ALSA thing, so I can also dump them in MIDI1 format. So that's the UMP is the new MIDI stuff, while we still have a compatibility layer to expose them in the old ALSA sequencer. Oh yeah, I have a speaker. So I have recorded some notes here. I can just replay them. So yeah, that's basically Zephyr playing music. I can also send them directly from ALSA. But I can also replay a file like using a-play MIDI. So really nice. Okay, let's move to the next part. Network MIDI2, which is even more new. So Network MIDI2 was announced in late January at NAMM, which is a music-oriented conference, just 1 week before my presentation at FOSDEM, so it was very new. So as you might guess, we are just going to connect MIDI2 device to the network. You can see some advantage. First of all, you're no longer locked to a single direction like the MIDI out to MIDI in thing. You no longer have, if you use a USB MIDI, you may have seen some musicians, they have lots of controllers and they have 3 or 4 USB hub as a tree, and it's very annoying. It often gets locked in some way. So here we can simply use a network switch, connect all together. You can possibly in a studio reuse existing infrastructure like the existing cables, possibly go over fiber if you want, maybe go from a stage to the backstage, cover long distance, etc., etc. Wi-Fi possibly if you want. Yeah, everything's possible now. So in Network MIDI2, no big surprise here. We have one UDP port, which will correspond to one UMP endpoint. And optionally, the spec says that you can expose your service or your endpoint over DNSSD, so other network MIDI device can discover you on the network. And it's based on like a host, which will be listening to incoming connections. Not really connections because it's UDP, but yeah, you will see just afterwards. And the client, which is basically an inviter, the one which will initiate the discussion. So how that works, you will have the client, which will be inviting the host. The host then accepts the connection, and now the session is established. So you can simply exchange some UMP data, like MIDI. And finally, one of them can send a bye, and the session is now closed. As you can see, there's a hole here, and that's because in Network MIDI2, you can also have an optional authentication. So how that works, if you invite a host and it requires authentication, the host replies you with a nonce. You hash that together with the credentials, which can be either a shared access key, shared by everyone, or a user plus password. So you just take the SHA-256 of that, send that to the host, and then the flow continues. So, as I said, it's conveyed over UDP. In UDP, the packet format is simply every time it starts with a MIDI in ASCII, so these characters in pink, and then it's followed by one or more so-called command packets. So a command packet is defined by the Network MIDI2 protocol. And this, again, consists of one header of 4 bytes, the command code, then the length field, and then some command-specific data depending on the command code. And these command packets basically divide into 2 categories, like session management, to invite, to close the session. There are also some things to NAC a packet or to ask for a retransmission. And the other category is like the data transfer, UMP data. Yeah, we can look at the packet layout, but I'm not sure it's very interesting in that case. But anyway, that comes from the spec. So we have 2 different packets on the top right. The authentication required, so when the host tells you, you must authenticate. And on the bottom left, we have UMP data. So this is new in Zephyr. It's still being reviewed. It's the pull request number 93923. And I hope we can get that soon in Zephyr, maybe 4.3, I hope. So to use that in Zephyr, as in my pull request, first of all, we enable some networking, IP networking. So config networking, either IPv4 or v6, and then we enable NetMIDI2 host. So currently there's only support for the host, so the thing that will accept incoming connection. Maybe later we could add some initiator or client. Then we use that macro to declare a UMP network endpoint. It has a name, and we give it a name in the C code, so we can reuse that variable later on. Then we can attach a receive callback, like in USB MIDI. And finally, we can start the host, which will serve connections. So to exchange some data, we can have our receive callback. We can simply log when we receive a UMP. And to send some data, we have 2 methods, either netMIDI2 send, to send to a single client, or netMIDI2 broadcast, to send to all connected clients at once. And finally, Zephyr has DNSSD already built in. So if we want, we can simply also enable that and use the macro existing in Zephyr, DNSSD register service, and now our MIDI2 endpoint is also discoverable on the network. Finally, there's a thing in MIDI2 which allows to discover the topology. So as I've shown you, there's this UMP endpoint. But how do we know what are the inputs and outputs available? So if I have my computer here, I have some synthesizer, they can communicate with the message type F, which is called UMP stream. So in UMP stream, basically, the client will say, hello, who are you? And the thing will respond like, I'm keyboard. And also I support that set of features. And then I can say, okay, so send me the information about your topology, and the thing will respond, and I can myself make a picture of what's the topology of the device. In USB MIDI2, it's not really required because that information is also available through the USB descriptors, but in network MIDI2, we need some way to expose that information. So how that looks, this is again a UMP packet, so something you can transport over USB or UDP. Basically, that's the endpoint discovery message, message type F for UMP stream, and then we have here a bitmap of what we request as information. So, for instance, if I request your name, then the thing will respond me with its name in simply ASCII. And if I ask for the endpoint information, it responds with like which version of UMP I'm supporting, the number of function blocks currently defined in the endpoint, whether it supports MIDI1 or MIDI2, and jitter reduction timestamps, which I'm not covering today. And similarly, I can ask for the function block, like asking, hey, function block 1, what is it? And it will answer. Again, you see a bitmap to ask for either the name or the function block information. And in that case, we have which direction is it, what is the group number, and how wide it is in number of UMP groups. So an example discovery. So I have my computer on the top left, a device on the top right, on the bottom right. So first I say, okay, tell me your name and information. It answers with hello. I have 5 function blocks, and I support both MIDI 1 and 2. My name is Zephyr. Then I ask, okay, so tell me all you know, tell me all your function blocks. And it can say, okay, function block number 1 is MIDI2, input outputs, and it covers UMP groups 1, 2, 3. And you have also the second function block there, but yeah, you get the idea. So we need that in Zephyr too if you have network MIDI, right? So there's also a new lib, which is called the UMP stream responder. So first of all, we can grab an existing description from the device tree we saw in USB MIDI, so we can simply reuse that information. Then we have a struct responder configuration, which says which device are we going to send the answer to, the method to use, because in network MIDI2 you can either broadcast or send to a single client, and also what's the endpoint, UMP endpoint specification, so what are the inputs, outputs available. And then finally, when we receive a message, we can, in case of a UMP stream, simply use the UMP stream responder to handle that automatically, and so Zephyr will just do that automatically for you. You don't have to do anything by hand. But still, you remain in control because you call it from your application code, so it's not hidden somewhere in the layer. But that's open to discussion if you have a better opinion. So again, I have a small demo. It will be even much faster. I have here the demo from the pull request in Zephyr. It starts a UDP MIDI2 server on that port, and I can run here. Yeah, MIDI2 is not yet supported besides USB in the OS level, but I have some Python script, so I can just run, find my thing, and you can see that it has discovered everything. So it's connected to the endpoint, and then it used the UMP stream responder to discover the topology I had described in my device tree. Yeah, small demo. Also, just mentioning it, but there's also MIDI CI, which allows to exchange some profile configuration information, like which attributes in the MIDI2 not on of events does your device support, like the orchestration profile or pitch 709. So as a recap, MIDI2 extends MIDI1. We can use Zephyr to build all of that. So we have either on top of USB device next, the USB MIDI2 class, or on top of the UDP sockets, we can build network MIDI2. We can leverage that to have the universal MIDI packets and then exchange some different kinds of MIDI data. Yeah, it was very easy to build that on top of Zephyr. So what's currently the state of things? So the universal MIDI packets and USB MIDI2 was merged in Zephyr 4.1 in March. So it's already standard. Network MIDI2 is currently being worked as well. So it's the pull request I've mentioned, as well as the UMP stream responder. And to the best of my knowledge, this would also make Zephyr the first open source operating system with network MIDI2 support. I mentioned MIDI capability inquiry, that's not very important. And then we can expect the MIDI association to specify Bluetooth MIDI2 soon. And in that case, Zephyr would have anything needed to do that as well. And so that's all for me. Thank you very much for attending. Yeah, MIDI2 is very new. Zephyr has everything needed, so let's just make things. Probably if you have many MIDI2 devices, it will also force desktop OS to support it and enhance the support. And if you want to reach out, you can simply use that these social handle. And I'm not sure if we may have 5 minutes if you have some question or remarks.
Are there tools for interacting with hardware, since like packages for talking with like the standard MIDI connector?
So the question was, are there tools to interact with hardware or standard MIDI1? So basically, MIDI1 is simply a UART. So if you get a packet from USB MIDI or network MIDI, you can simply just write that out to the UART. If it's a MIDI2 message, you still have to downscale the velocity, which is from 16 to 7 bits. But yeah, that's very basic transformation, and you simply pull that out on the UART using the Zephyr. So that's even what's in the sample you can see in the pull request. I do that, so you can just look that up. And you can do pretty much the same. If you get a UART in, you just yeah, wrap that in a UMP packet and send it in your preferred way.
Yeah, thanks for your work on MIDI and Zephyr. I will definitely have a look and use it. I was just wondering if you have an idea of the latency and jitter while sending out MIDI notes or other messages with the USB.
So over USB, you're still limited by the USB time slots because the host is timing the whole bus. But it's I don't have any precise equipment to do such measurement. But it's down to probably 1 millisecond or something, which is the USB time slot. On network, it really depends on the network layer you are using, like on fast Ethernet, if you connect that directly to your computer. If you're over Wi-Fi, you can experience some large jitter. But anyway, in MIDI2, there's a thing called jitter reduction timestamp. So every message can be annotated along with a reference clock that is sent periodically. So I'm not sure how that can be leveraged in live performance because, yeah, it's live. But if you are recording, that can make some very precise timing because you can have timestamp all along the way to make that into a recording.
I've played a little bit with MIDI1 on user space Linux, and most of the APIs have a timestamp that's associated. I believe it is to work around scheduling. That means that the packet might have arrived a few milliseconds ago. I think that's right. You correct me if I'm wrong. Did you have to introduce the same timestamps in your APIs on Zephyr or no?
So no, in Zephyr, there's nothing associated to timestamp or anything, and in Linux, I think it's done in at the other level. So it's not at the protocol. There's nothing that sends the protocol. In MIDI1, the only thing that can help is, again, you have the MIDI clock. So it sends, I don't recall the frequency, but I think it's 24 times per beat. And so this also allows either to synchronize like the tempo between different devices for audio effects that are time dependent, but also maybe to have a better synchronization or reduce jitter in case. But on a serial link, I don't really see how you can have large jitter or latency unless maybe you are using UART over AVN carrier or something. But
one of the big problems with MIDI1 is just having 16 channels and having channel conflicts, difficult interfaces to change that. Does MIDI2 spec somewhere in the arena uses yes or no? Does it have a way for devices to negotiate that without user interaction?
so the question was, in MIDI1, there's only 16 channels, and it can be very constraining. So does MIDI2 have a solution for that? So first of all, as you've seen, in MIDI2, we have technically 256 channels because 16 times 16. Also something not in Zephyr yet because I have no use case for that. But in MIDI2, you can also have, through UMP stream, you can reconfigure which function blocks can be activated or not. So you can have more definitions that what's actually available. And so you can say, okay, I have 2 function blocks on that group, and I can enable either one of them, for instance. So you can have things. Not sure if that's done automatically or not, because, yeah, the user may want still to select what's available. So I'm not, yeah, it really depends on the use case.
It's turning 4 dip switches into 8 or 10 or something, though. So
Yeah, still better than the physical switch you have in the back of your synthesizer.
Is your work being used by vendors? Are you being paid for that? And do you know of anyone that's interested in Zephyr support for that?
So I haven't heard of any vendor. I've seen some other hobbyists doing things with that. I'm doing this mostly as a personal project because I'm working with a friend who is a musician, and he just wanted to have things. I had Zephyr on one hand, and yeah, Fusion. That was basically the point. And Network MIDI2 is actually because, for me, the main arguments was the, like I mentioned on the first slide of the network, like reusing all network equipment and stuff and not being limited by the unidirectional serial link or by the USB hub hell, which my friend has experienced many times.